remember. So for quantitative aspects, let me just, okay, so we said that we have four formulas that we're working with. So this is essentially stoichiometric calculations. But we said a mole, this is a word or a name that represent a number, right? It's a word or a name that represents a number. And which number is that? The number we're referring to is 6,023 times 10 to the power 23. So when we say 1 mole of something, it means you have 6,023 times 10 to the power 23 of that thing. So if we say 1 mole of oranges, if we say 1 mole of oranges, we mean 6,023 times 10 to the power 23 oranges, which is a huge number of oranges. So similarly, if I say 1 mole of hydrogen molecules, of H2 molecules, that tells me that I have 6,023 times 10 to the power 23 molecules of H2. And that is a huge number of molecules. And remember, one molecule is something like this. You have a hydrogen atom that is bonded to another hydrogen atom. So think of these things, 6,023 times 10 to the power 23 of them. That's quite a huge number, okay? And you won't finish today if you try to draw those number of molecules. So a mole is a name that represents 6,023 times 10 to the power 23 things. But remember the formal definition that you're going to be asked in the exam. They're going to ask you to define what is 1 mole of a substance or a mole of a substance. Then you're going to tell us that it is the amount of substance, amount of a substance so it says is the amount of substance having the same number of particles as there are atoms in a 12-gram carbon 12. So this is a definition that you will be required to give in the exams. So 1 mole of a substance is the amount of a substance having the same number of particles as there are atoms in 12-gram carbon 12. And just to quickly explain this statement again so that it makes sense when you read it, remember that carbon 12 is a carbon that has an atomic number of 6 and a mass number of 12. Now, specifically, we are being specific that we are talking about carbon 12. This is because there are other carbon atoms. Remember that in grade 10, you learned about what we call isotopes, right? And remember, isotopes are atoms that have the same number of protons but different number of neutrons, which means they have the same atomic number but different mass number. So carbon does exist in other forms. You find that you have C6, maybe there's the mass number there perhaps maybe is 14, or maybe you have maybe you have 10. You understand? So the mass is different, but the atomic number is still the same. Remember, what determines what type of atom we're talking about is the number of protons. If you change the number of protons, that's when you change the atom. It may no longer be carbon. If you can put 5 here, it's no longer gonna be carbon. You understand? It's now going to be boron, because boron is the one with 5 protons. So what we can only change is the mass number due to the number of neutrons, and it will still remain as carbon. So therefore we become specific that we are referring to carbon 12. That's what this statement is saying. But we have 12 gram of that carbon 12. Ne? So if you have 12 gram of this carbon 12, what we can say is that Avogadro measured how many atoms. Remember, one atom of carbon is going to have a nucleus with protons and neutrons, and then it's going to have electrons outside. Understand? It's gonna have electrons outside like this. So here's a carbon atom. In a 12 gram of this carbon 12, how many atoms do you have? How many atoms do you think we have in a 12 gram of carbon 12? Anyone who can guess? 5, 10, 100, 1,000? Well, turns out that when... Yes, Mr. Kevin? 6. Okay. In 12 gram of carbon 12, ne, the number of atoms that are there, turns out that Avogadro found out that there are 6,023 times 10 to the power 23 atoms. That is the number of atoms in just a 12 gram of carbon 12. Then Avogadro decided to name this number. He gave it a name and he called it a mole, or specifically 1 mole. He called it 1 mole of 1 mole. So in 1 mole there are 6,023 times 10 to the power 23 atoms in a carbon 12, in a 12 gram of carbon 12. So then he said all other atoms or elements are going to be measured using this standard name, or rather using this 1 mole. So all of them are now going to be measured in terms of 1 mole. So therefore that's why we call this Avogadro's number, and it's a constant, so therefore it's written as Na. It's a constant. So when you say 1 mole of something, when you say 1 mole of something, you are saying it is the amount of that thing, ne? It is the amount of of a substance, or the amount of that thing that has the same number of particles as the number of atoms in a 12 gram of carbon 12. So to keep it simple, when you say 1 mole of sugar, you are saying 6,023 times 10 to the power 23 particles of sugar. So 1 mole of anything, it's this number because of that. So I hope that is clear. So 1 mole of anything just means that number, okay? Hence we say it's a name that represents a number. So if I have 2 moles of something, it means I must multiply this by 2. If I have 3 moles of something, I must multiply this by 3 so that I get how many of that thing we have. So that is what we have. Let's have our first example in terms of how we can use that. Let's say we got a question which then requires us to find the following. It says calculate the number of moles of water in 100 grams of water. We need to know how many moles of water are in 100 grams of water. So the first thing you want to do is to say, okay, since I'm given the mass, I'm going to use what? N is equals to small letter m over capital letter M. Now you must remember also that you are dealing with water, which is H2O. So the number of moles of that H2O is going to be its mass divided by its molar mass. Its molar mass is going to be 1 times 2 plus 16, of which, remember, molar mass you find in your periodic table. Then I believe the answer should be 5,56 moles. Those are the number of moles of water in 100 grams of water. So wait, what if a question comes and says calculate, okay, let's say calculate the number of molecules in 100 gram of water. What if the question comes in this way? How are we going to solve it? Calculate the number of molecules in 100 grams of water. Exactly, that's very much correct. So we would need to find the number of moles first. Why getting number of moles? Because once we know the number of moles, we can multiply them by the Avogadro's number. Then we'll get how much of the molecules of water we have. Because remember we said 1 mole of, if you were to say, remember that, let me write it like this. Remember that 1 mole, literally 1 mole of H2O molecules. 1 mole of H2O molecules is 6,023 times 10 to the power 23 molecules of what? Of H2O. 1 mole of H2O molecules is that number of molecules. Same as when we said 1 mole of oranges is that number of oranges. So here 1 mole of H2O molecules is that number. But then the question becomes, if 1 mole of water is this number of molecules. Remember, 1 molecule is like this, ne? You have H, and then another H, and then you have oxygen. You have oxygen. This is just 1 molecule. Okay? This is just 1 molecule. So, when I'm saying I have 1 mole of H2O molecules, that means I have this number of molecules. Of this, it's a lot. It's like 6,023 and then 0,000,000,000,000,000. You understand? And then molecules of water. So you can see that 1 mole is a lot of molecules. So now, if they ask me now that how many moles, what is the number of molecules in 100 grams of water, I cannot come here and say 100 grams. I cannot come here and say, oh, so I have 100 grams of water molecules. So now, how many molecules will we have? No, I cannot say that because we measure in moles. We don't measure in mass in terms of, getting the number of molecules. I actually need to know the number of moles of water that I have. So how do we calculate that? So like said, we can simply use this formula that has mass. Ne? Then the mass is 100. The molar mass is going to be 1 times 2 plus 16, and then you're gonna get 5,56 moles. Right? Now you have the number of moles of what? Of H2O. So now you can then come here. You can then come here and say, so 5,56 moles it's going to be how many molecules? You see, so you say 1 mole is that, so 5,56 mole is how much? You see, you can even call it X. You can even call it X. Then you cross multiply. X times 1 is X. Therefore, it's going to be 5,56 times 6,023 times 10 to the power 23. And then if you have your calculator nearby, please just tell me how many molecules is that. Great. So you can see that it's a lot of molecules. 1 mole is 6,023 times 10 to the power 23. But 5,56 moles is 3,35 times 10 to the power 24 molecules. 3,35 times 10 to the power 24 of these things. It's a lot. It's a lot. So, now that you understood what we are doing when we are saying what is a mole and stuff, we don't have to use let me just remove this. So now, since we are used to formulas, you don't have to do this cross multiplication. You can simply use the formula n is equals to n over Na. What this formula will do is that since you have the number of moles, right, as 5,56, you substitute them, and then n will stand for the number of particles, which means the number of atoms or the number of molecules depending on what you are looking for. So, and then this one is going to be the Avogadro's number, which is this. And then you will see it's more like cross multiplication, but still you're going to get 3,35 times 10 to the power 24 molecules. You see, that's how many molecules we have in 100 grams of water. So if I ask you, calculate the number of molecules in 200 grams of water, you know that you have to change the 200 to moles. Then once you have the moles, you put them here, then you'll be able to calculate how many molecules we have. I hope that it's clear. Any question? Okay, great. So that's what we have there. Now let's try this one out. Now it says calculate the molar mass. Calculate the molar mass of a 5 mole substance with a mass of 295.5 grams. How would you answer this? Right, great. So you can say N is equals to M over capital letter M. So the number of moles, when you say 5 moles of a substance, we already gave you the number of moles of that substance. So you just simply have to substitute that 5 mole here. But the mass is also given that it is 295.5 grams. But we are looking for the molar mass. So this is your molar mass there. So you cross multiply, or you can cross multiply. Then you'll have 295.5 is equals to 5m. Then you divide by 5 both sides. So what would be your molar mass? I believe it should be 58.5 grams per mole. It's important to use the correct unit. So the unit is grams per mole. That is the molar mass of that substance. Right. No. You cross multiply and then you divide by 5. Great. Let's try this one. So try this one. It says calculate the mass of NH3 with 0.15 moles. Calculate the mass of NH3, the mass of ammonia, with 0.5 moles. So I believe we can also see in this case that we are dealing with mass, so we shall use the formula small letter m over capital letter M. So are we given the moles? Oh yes, it's given that it's 0.15. Are we given the mass? No. But what is the molar mass? Now remember, NH3, you can calculate its molar mass from the periodic table. So for nitrogen, what is the mass of nitrogen? I believe it's 14. And then what about hydrogen? For hydrogen it's 1. But there are 3 hydrogens there. So you multiply by 3. So therefore you shall say you have 0.15 small letter mass, and then you have 17. So therefore your mass will be, you cross multiply again, and then you shall have 0.15 times 17. So what would be the mass of NH3? I believe that should be 2.55 grams. Please verify these with me. If you're getting a different answer, please do tell me. Otherwise, that's how you would get the mass. So I'm pretty sure that at this point you are very much confident in using the formula N is equals to M over M. Understand that the number of moles are crucial in answering this type of questions, but it's also a nice formula to use to get the number of moles of a substance. Whenever you are given the mass of a substance, you calculate the molar mass from periodic table, and then you can get the number of moles of the substance, of any substance there. Right. Then we come to Avogadro's law. is Avogadro saying in his law? Is there anyone who understands Avogadro's law? You ever heard about it? That there is a constant, right? At least that's a good start, man. That's a good start. So here's Avogadro's law. If you need to state it, this is what you say. Avogadro's law determines that 1 mole of any gas occupies the same volume at the same temperature and pressure. 1 mole of any gas. What are we saying there? Right? Understand the following. 1 mole. When we say 1 mole, what do you remember? What do we mean by 1 mole of any gas? Anyone? So what I want you to tell me is that when I'm saying 1 mole of any gas, without going to the definition of 1 mole, understanding what is 1 mole, then what would be 1 mole of any gas? One mole is not Avogadro's constant. No, my question is, if I'm saying 1 mole of any gas, what do I mean? What am I saying? Nesha. No, but thanks. You're there. You're there. I'm sure you're gonna get it. Any idea, Miss? Is that Miss Ori there? I see Miss Ori and Miss Andile also. Do you have any idea of what is 1 mole of any gas? What it means? What are we saying when we say 1 mole of any gas? Okay, think of a dozen. A dozen is a name, right? That represents what? 12. When I'm saying a dozen of eggs, what am I saying? I'm saying 12 eggs, right? When I say a dozen of t-shirts, I mean 12 t-shirts. When I say a dozen of apples, I mean 12 apples. So a dozen is a name that stands for a number. Which number is that? 12. Similarly, 1 mole is a name that stands for a number. And which number is that? It's the Avogadro's number. Do you understand me? A dozen stands for 12. 1 mole stands for 6,023 times 10 to the power 23. Okay, so whenever I'm saying 1 mole, it is a name that stands for that number. So when I say 1 mole of t-shirts, I mean 6,023 times 10 to the power 23 t-shirts. Same as a dozen. I'm sure it makes sense now. So when I say 1 mole of any gas, what I mean is that 6,023 times 10 to the power 23 particles of any gas, meaning molecules, because a gas usually is a molecule. For example, we talk about a chlorine gas, which is Cl that are bonded. So you have chlorine there bonded to chlorine. This we call it a molecule, right? So we are saying that 6,023 times 10 to the power 23 molecules of chlorine and 6,023 times 10 to the power 23 molecules of hydrogen gas. Ne? Remember, one molecule of hydrogen gas is this. So we're saying 6,023 times 10 to the power 23 molecules of hydrogen and 6,023 times 10 to the power 23 molecules of chlorine and 6,023 times 10 to the power 23 of any other gas. Ne? It occupies the same volume, which means 6,023 times 10 to the power 23 of chlorine occupies volume V. Let's say that volume is X. It means 6,023 times 10 to the power 23 of hydrogen molecules are also going to occupy what? Are also going to occupy volume X. The same volume. And 6,023 times 10 to the power 23 of any other gas is going to occupy volume X, provided that those gases, so this is like you having containers. This is a container for hydrogen molecules, this is a container for chlorine molecules, and then this is a container maybe for nitrogen gas molecules. So we're saying all of these gases are going to occupy the same volume. So when I measure the volume for hydrogen, that volume is going to be the same as the volume for chlorine. It's going to be the same as the volume for nitrogen. But provided that they're at the same temperature and pressure. So provided that they are at the same temperature T and pressure P. So for them to occupy the same volume, they must be at the same temperature, and then they must also be at the same pressure. That is Avogadro's law. So let's repeat it again. 1 mole of any gas, right? Which means 6,023 times 10 to the power 23 molecules of any gas is going to occupy the same volume. They are going to all occupy the same volume, provided that those gases, they are at the same temperature and pressure. So that means the temperature for hydrogen, it can't be 10 degrees Celsius, whereas the temperature of chlorine is 5 degrees Celsius. No. They must all be at what? At 10 degrees Celsius, at 10 degrees Celsius. The pressure for hydrogen, it cannot be 2 pascals, whereas the pressure for chlorine is 5 pascals. No. The pressure must be the same, right? It must be 2 pascals, and then here also 2 pascals, and then there 2 pascals. If those conditions are met, that they are at the same temperature and at the same pressure, then those gases, 1 mole of them is going to occupy the same volume. Do we understand Avogadro's law? Mr. Kevin, did you get it? Perfect. I'm glad. So that's what we're saying. 1 mole of any gas is going to occupy the same volume, provided that they're at the same temperature and pressure. So, if that is the case, what if their temperatures are as follows? So let's say this, right? So let's say this. Let's say that the temperature is as follows, and then the pressure is as follows. Right. Let's see. Um, mm, mm. Right. So, what if the temperature is minus 0.15 degrees here, degrees Celsius, and then here the temperature is also the following, and then here the temperature is also that. And then what if the pressure, right? What if the pressure is 101.01 times 10 to the power 5 pascals. 1.01 times 10 to the power 5 pascals. 1.01 times 10 to the power 5 pascals. What if the temperature is like that? Do we agree that the temperature is the same? Yes. Do we agree that the pressure is also the same? Yes. Then therefore, all of those gases, 1 mole of them is going to occupy the same volume. So how much volume do they occupy if the temperature is like that and if the pressure is like that? Specifically for this temperature and pressure, listen carefully what I said. Specifically for this temperature and pressure, the volume that these gases are going to occupy, the volume that the gases are going to occupy is going to be 22.4 decimeter cubed. 22.4 decimeter cubed. 22.4 decimeter cubed. So all of the gases, 1 mole of them is going to occupy 22.4 decimeter cubed at that specific temperature and pressure. Then we give this temperature and pressure a special name. We then call them standard temperature and pressure. So at standard temperature and pressure, 1 mole of any gas is going to occupy 22.4 decimeter cubed, which tells us that if the temperature is not negative 0.15 for all of them, let's say if the temperature is 20 or 10, the volume is not going to be 22.4. The volume is only 22.4 if the temperature is negative 0.15 and if the pressure is 1.01 times 10 to the power 5. By the way, negative 0.15 degrees Celsius in kelvins, Mr. Kevin, in kelvins, it's going to be 273 kelvins. 273 kelvins. And then 273 kelvins. So in kelvins, it's going to be 273. So if the temperature is 273 kelvins and the pressure is that, then the volume that the gases are going to occupy, 1 mole of those gases is going to be 22.4 decimeter cubed. Therefore, that standard temperature and pressure is what we call STP. Okay, so at STP, that is what is happening. Okay, you don't need to know a lot of these things. Let me just summarize whatever I said in a simple Zulu. So in Zulu, what I'm saying is that whenever you are working at standard temperature and pressure, the molar gas volume, which is the volume occupied by 1 mole of the gases, it's going to be 22.4 decimeter cubed. So that is what you're gonna use here whenever we're dealing with STP to get the moles of the gas. Okay, so that's simply what I'm saying. At STP, for VM we use 22.4. But if the temperature is not at the standard temperature and pressure, You don't use the 22,4 there. They must give you the molar volume. So check out the question whether you are not given molar volume. Okay, that's it. I hope that's clear, and then we're gonna practice that on a certain number of questions. Just 2 questions that I have for you today on that. Ne? So let's start with 4.1. Let's start with 4.1. 4.1 says determine the volume of 0,2 moles of hydrogen gas at standard temperature and pressure. Now, listen. We said 1 mole is gonna occupy 22,4 decimeter cubed at STP, right? According to Avogadro's law, 1 mole of any gas occupies the same volume at the same temperature and pressure. But we said if the temperature and pressure is the standard temperature and pressure, then 1 mole of each gas is going to occupy 22,4 decimeter cubed. So now that we have 0,2 moles, oh guys, I shouldn't be writing this. Yeah. So if we have 0,2 moles, how much volume is it going to occupy? Since we are still at STP, how much volume is it gonna occupy? So we shall say x, then we cross multiply, then it's going to be 0,2 times 22,4. Okay? What do we get as the answer? I believe we should get 4,48. Is it correct? Great. 4,48 decimeter cubed. So that is how much volume is occupied by 0,2 moles of hydrogen. When it is for 1 mole, it occupies 22,4, but for 0,2 moles, it occupies 4,48. But you don't need to do that. As long as you have the formula, you can use the formula. You can simply say, since we're working at STP, we say N is equals to V over Vm. Remember, at STP, Vm is equal to 22,4 decimeter cubed. So you then say, okay, the moles is 0,2. I don't know how much volume it occupies, but I know that the molar volume is 22,4 at STP. So therefore, the volume is going to be, you cross multiply. 1 times V is V. Then you're going to have 0,2 times 22,4. Then it should give you 4,48 decimeter cubed. That is the amount of volume that is occupied by hydrogen at STP. Give this one a try, and as soon as you are done, just give me a thumbs up that say I'm done, and then we can take a look at it. But please note the following because okay, it's fine. Try to do it first. Let me see if you'll be able to do it. It might be a bit long, but yeah. Try that one. I'll give you just 3 minutes for that. So I'm just gonna put a counter here, at a timer here, and it's gonna tell me, say, they are done. Once 3 minutes hits. Yeah. And the time starts now. This stopwatch is like a microwave. When it is finishing here, hi. But guys, are you winning? Are you done? Please tell me how far you are. Ah, perfect, perfect. Um, what about you, ladies? Anyone who's done? Okay, okay, no problem then. Oh, okay, great. Mr. Kevin, can you please send me a picture, remember, of what you have, ne? Same goes for you guys. As soon as you're done, so you can just send me a picture there, so that I can check um how you guys are solving these. Okay, I was l- I was looking at it. Um, I was looking at it, ne? Very nice. Just don't forget to write units on number of moles, there, ne? Where you calculated number of moles. Just don't forget to write the unit. The unit is mol, which is mole. And then where you substituted there, don't put dm. Ne? Don't put dm. Just put the numbers only. Okay. Otherwise, looks very nice. Uh, Right. Okay, so we can take a look at that. Yeah? Um, so the first thing here, we need to check what the question is saying or what it wants, right? The question wants the mass. It is looking for mass. And if a question is looking for mass, then let's remember that the only formula that has mass is this one. M over capital letter M. Right. But for me to get the mass, I need the number of moles, right? Because the molar mass I can calculate for NH3. For N is 14, and then hydrogen is 1 times 3. Okay, so I have 17. But do I have the number of moles? No, I don't have. How can I get the number of moles? What can I use again to get number of moles? Well, we're given the volume. So if you are given the volume, you remember Avogadro's law. But before we use this volume, let's remember that to move from centimeter cubed to decimeter cubed, we divide by 1,000 because we work in decimeter cubed. By the way, you can also be given in milliliters, ne? You still do the same thing. You divide by 1,000. So now I will use Avogadro's law and then say, okay, I don't know the number of moles, but the volume that this gas is occupying, it's 60 divided by 1,000, which I believe is 0.06. And then remember it's at STP, so therefore we're using 22.4, right? Then we get the number of moles to be 0.0027 moles. Please round off to 4 digits because it is not the final answer. Then we take these number of moles, we now put them here. We say 0.0027, and then when you cross multiply, your mass becomes 0.0027 times 17, which gives you 0.05 grams. I don't know if you got the same thing, let's see. But that's what we should have. So please, Mr. Kevin, keep it at 0.0027. I saw that now you wrote 2 comma something. And then let's see, Miss Uri, 0.27. Oh, Miss Uri, it's like she didn't convert well. You saw it. Ah, perfect, perfect. Yeah, yeah. So, I hope that you understood that, guys. So that was a combination of what we talked about first, and also how to incorporate Avogadro's law. I hope that is clear. So please keep practicing and do a lot of questions. I'm gonna send you a document with a lot of example questions and some practice questions. So please look out for that. And if you're facing challenges, you tell me. Otherwise, have yourself a great weekend and stay safe.